Next, we're going to introduce the notion of deterministic sequence. A bounded sequence f from n to c is called deterministic if it has topological entropy 0. Now let us briefly recall the meaning of topological entropy for a bounded sequence. So I copied the definition for topological entropy right here. What does it mean for a bounded sequence to have topological 0? Or in our new terminology, deterministic. It means, let us do some modification for this statement. F has topological entropy 0 if for any sigma greater than 0. And for any epsilon greater than 0, the sequence of vectors f of n plus 1 through f of n plus m, where n ranges over all natural numbers, is contained in Cm, can be covered by big O exponential of sigma times m plus little omega of m, many balls of radius epsilon, under the L infinity metric as m goes to infinity. Okay, as I promised, I shall give you an example for topological entropy of a bounded sequence. Now I shall give you a classical example of a deterministic sequence. The example is as follows. So look at this sequence. The sequence e2 pi I p of n where n ranges over all natural numbers, where p of n is a polynomial with real coefficients, is deterministic. Namely, of 0 entropy. So now let's prove this. Our goal is to show that, recall the definition, for any sigma greater than 0 and any epsilon greater than 0, the sequence of complex vectors, so look at this sequence, e2 pi I p of n plus 1 all the way through e to the 2 pi I p of n plus m can be covered by big O exp of sigma times m plus little omega of m balls of radius epsilon. And to this end, we look at the binomial expansion in Pn plus L for L greater or equal to 1, less than or equal to m. So we'll look at the binomial expansions of them. P of n plus L is equal to the summation from k to 0 to d of ak times n plus L raised to power k. And this can be expanded as a polynomial in L with coefficients that's denoted by bkn. So this bkn might be some really complicated coefficients in this sum. We don't really have to care about what bkn's really are. But, so this is for L greater than 1, less than or equal to n. So now, let's focus on those coefficients bkn's. So now look at the coefficients. So this is a vector in Rd plus 1. Those numbers can be very, very large or very, very small. But remember, those numbers as this polynomial should appear in the exponential indices, because e raised to the power e2 pi I x is a periodic function of period 1. So at this point, we only have to worry about the value of those numbers, those coefficients, mod 1. So due to the periodicity of e2 pi I x, we can take them to be numbers in the interval from 0 to 1, mod 1. Okay, now let's go back to look at this definition here. Now we have to figure out the meaning of covering balls in this setting. So now, given epsilon greater than 0, what does the epsilon covering balls look like? We know that their centers the centers of those epsilon covering balls should be e raised to 2 pi I times CD times LD plus CD minus 1 times LD minus 1 all the way through C0. To make the balls centered here to form a epsilon covering balls for this sequence of vectors, we really want those CD minus 1 all the way to C0, we want those CIs densely chosen. If they are densely enough chosen, then we should expect those balls with radius epsilon to form a covering of the sequence of vectors. But how dense? To figure this out, we look at this difference. Remember, This part is precisely our Pn plus L. So this difference, if you use an elementary inequality for complex numbers, this will give you 2 pi times the sum from k to 0 to d of bkn minus ck, its absolute value, times L raised to power k mod 1. And here we are using this elementary inequality in complex analysis, or just the elementary complex numbers. You can verify this by just drawing pictures and find out the geometric meanings of left-hand side and right-hand side. So you have a unit circle, and you have two angles. One angle is 2 pi x, and the other angle is 2 pi y. The left-hand side refers to the length of this, and the right-hand side refers to the length of this arc. Geometrically, it should be clear to you why this inequality is true. Okay, with this inequality, with this upper bound, you can see how those CIs should be densely chosen. So we need to make sure the pool for the choices of CKs is so dense that the sum is less than epsilon. Technically, we divide the unit interval from 0 to 1 into capital N many intervals of equal length. With n, now we have to be a little bit careful about choosing this n. We choose n to be 2 pi times d plus 1 times m raised to power d times 1 over epsilon plus 2. This is not integer, so we take the ceiling to make this generous. And it follows that with the property choices of CKs, we can make sure this absolute value is bounded by 1 over n mod 1. So mod 1, left-hand side will be bounded by 2 pi times. And now you simplify this. Note that this k is bounded by d, this L is bounded by m. After simplification, you will realize this is less than epsilon. So the difference is bounded by epsilon, with appropriate choices of CKs. What appropriate choices? With CK chosen to be the closest element in script C to BKN. That is our choice for CK. Now recall that we want to find the covering for this sequence. What is that covering? Now we take our covering to be the balls, the epsilon balls centered at those vectors. And it's not hard for you to see that the indeed from an epsilon covering of or sequence of vectors with respect to L infinity metric. Every vector in here is within epsilon distance with respect to L infinity metric to at least one member in here. That follows from our discussion above, this inequality. And you should observe that we can actually, so in each of those M components, we are using the same set of CKs. So CK here is the same as CK here. That is because in our bound above, the CK is chosen independent of this L for any L from 1 to M. For any L from 1 to M, we always get the upper bound epsilon. So that is why we can have same CK in each of those M components. Now, if you denote this set by C tilde, the cardinality of C tilde will be same as the cardinality of epsilon ball covering for this sequence. So now let's give an estimate for the cardinality of C tilde. This guy will be less than or equal to the cardinality of C raised to power D. But what is the cardinality of C? Recall by our construction, the cardinality of C is n, or n plus 1. It doesn't matter. So this guy is bounded by n plus 1 raised to power d. Now we plug in the expression for n. This is n plus 1 raised to power d. You know this is a polynomial in M. That means this quantity must be a big O of exponential of sigma m plus little o of m. This is a polynomial in M, but this is an exponential thing in M. For any sigma greater than 0. This means we get 0 entropy by our definition, since this is any epsilon greater than 0. And thus, it is deterministic. And we are done with this example.